Hello and welcome again. In this video, we'll talk about the linear congruential generator. This is another way to produce pseudo-random sequences of numbers. I remember last time we talked about the middle square method to do that. So this linear congruential generator will also generate a pseudo-random sequence of numbers, and in this case, it will be integers. Now, the problem with that is that this is not cryptographically secure. So whenever you want to use this generator for some cryptographic applications, you wouldn't use this linear congruential generator. So what is this linear congruential generator about? So before we do that, I have to introduce some notation, and the notation is, it goes like this. So the notation is like this. If you have two integers, they call them a and m, any two integers. We're gonna denote by this here, a mod m. You're gonna read it like that, a mod m. That's gonna be the remainder when you take the number a and divide it by m. So this is just an annotation here. So this denotes remainder. Whenever you see this here, it denotes the remainder of this integer divided by this integer, whatever the remainder is of that division. So let's see a couple of examples. So let's say, for example, I want to compute what is the 15 mod 2. So basically what I have to do is I have to take this number 15 divided by 2. Whatever the remainder of that division is, that is this number. This number denotes the remainder. So if you look here on the side, I have the whole thing set up. So I'm going to take 15 divided by 2. So if I do that, what happens there is 7 goes into 15. 2 goes into 15 7 times, and so 2 times 7, that's 14, so minus 14 here, and of course that subtraction gives me 1. So the remainder of that division, as you can see there, the remainder is just the number 1. So this expression that you have here, this one, denotes the remainder. So in this case, 15 mod 2 will be 1, so that will be equal to 1. So let me use another color. So this will be equal to 1. Okay, so that's basically just the remainder. Let's look at some other examples. So let's say I have -1 mod 26. So I have this. I need to make the division there. So I have to say I'm going to take the number -1 and divide it by 26 and look at the remainder of that division. So I have it set up over here. So -1 divided by 26. Now remember, this was one of the examples we did a while ago when we discussing the division algorithm. And remember that what that was is the following. 26 into -1 goes -1 times. Now if you don't remember how that was done, go back to the video of division algorithm and see how we got that number. Alright, so then -1 times 26 will be -26, but I have to subtract it from the -1. So basically what I have there is -1 plus 26. So that will give me, of course, 25. So that will be the remainder. So the remainder of that division is 25. What that means is that -1 mod 26, which is the remainder, would be exactly the number 25 in that case. So this is going to be equal to 25. All right, so this is just a notation we need to use to be able to make this linear congruential generator a little bit easier to read. So let's go down a little bit here. So before we actually go into that, let's look at some properties that's going to help us compute this a mod m a little bit better. So for this part, from now on, I'm going to assume that everything here is a positive number. So we're going to assume here that I have two numbers, a and m. Both of them are positives. Now, if this happens, if you have that a is strictly less than m, then a mod m means the remainder of a divided by m is exactly a again. Now you can check that with some examples. For example, here, so let's say I have this example 2 mod mod 3. So if I want to look at that example, what I need to do is I take 2 divided by 3. So take 2 and divided by 3. So 3 into 2 is 0 times. 3 times 0 is 0. And so I have subtract 0, so I get 2. So you get exactly the same thing back. You get this guy over here. That's the property. What the property is saying. Every time you have a less than m, and I'm assuming here that both a and m are positives, then this is going to be a mod m will be a again. As long as, of course, m and a are positive and a is less, strictly less than m. So that's going to happen all the time, this property here. The other property I want to mention is this one. If you have the number a and that number happens to be a multiple of m, means that a is some number times m, where that number is an integer, a product of m times some other integer. Then the remainder of this division a and m will be 0. Let's think about that for a second. So what happens if a is multiple of m? Well, then what happens is that m will go exactly into a. If m goes exactly into a, it means that the remainder, then in that case, will be 0. That's why you get a 0 there. So for example, let's look at an example here. So if I have, let's say I have 6 mod 3. So that will be the remainder when I take 6 and divide it by 3, because 6 is a multiple of 3. Because 6 is 2 times 3, then that is going to be 0. And of course, because when I take 6 and divide it, I take 6 and divide it by 3, the remainder will be 0. So that's why the property in this case is true. I'm going to erase this so you don't confuse that with a 6. That is a 0 there. 0. All right, so that's two important properties that I wanted to mention here, because it's going to make our computations a little bit easier if we use these two properties. Okay, so what is the congruential formula? So the recurrent is going to be a recurrence formula, and if you don't know what that means, don't worry. We're going to go into the details in a little bit. To set up the formula, what you need to do is you need to make a choices for 3 integers. So you're going to choose 3 integers. The integers we're going to name in m, a, and b, and these integers have to satisfy some properties. The first property is that m should be a positive number. Okay, so this is the first number. That number we're going to call the modulus, and you will see in a second why. Then we have to choose a number a. That number has to be again positive, and it has to be strictly less than the number you chose in number 1. So for example, if you chose this m to be 5, then your a should be less than 5 and positive. And it has to be an integer. And you have to choose another number b, and that number b, it has to be again less than the modulus of this m here. It could be 0 or it could be positive in this case. So you make a choice of 3 numbers, m, a, and b. And the next thing you have to choose is you have to choose another extra number, what we call the seed. So this is basically where the random number generator is going to start. We're going to start at this number here, x0. And the property for this number should be that you could start from 0. That's okay. X could be 0 or positive. But it has to be strictly less than the number you chose here, m. Okay, so you have to make a choice for 3 numbers. M, the modulus, a, the multiplier, b, that we call the increment, and you will see why they have these names, and x0, which is the seed. All right, so basically what the formula is right here. The formula is this formula here. This is a recurrence formula for the linear congruential generator. And let me explain a little bit what that means. So x0 here is the seed. So it's where the sequence of numbers is going to start. Exactly the same what happens with the middle square. You're going to start in some numbers. So the seed here doesn't have to be a 4-digit. It could be whatever you want. And this is a recurrence formula. So what this basically is saying is this. The next number, which is xn plus 1, the next number, will be equal to take the previous number, which is xn, multiply it by a, add the number b, and all this is going to give you a number, and then take the remainder of this number when you do the division of this divided by m. Okay, so let me say that again. So the next number, which is xn plus 1, is equal to the previous number multiplied by a, add b, and then take the modulus, means the remainder. That's why they have this number. So m is called the modulus because I'm taking modulus. A is called the multiplier because I'm multiplying by that number. As you can see here above, a is called here the multiplier. B is called the increment because that's exactly what I'm doing. I'm incrementing that number there with b. And so this is basically the linear congruential generator. So that's the setup. What you have to do here basically is you need to choose the values of a, b, and m with the properties I mentioned earlier, and you also have to choose the seed. So let's look at an example. So let's see how an example will look like. So let's look at this. So we have to choose some non-negative integers, m, a, and b first. So we could choose, for example, we could choose an m to be 13. The choice for a and b, remember, a has to be a positive number and it has to be less than m. So in this case, that happens. 4 is less than 13. And the b could be 0 or positive, and it also has to be less than the modulus than this number 13 here. So I have these choices here. So we made these choices. The next thing you have to do is you have to choose a seed for that random number generator. So what you're going to do is choose a seed. So we also choose the seed. And you can choose whatever you want as long as that number is less than the modulus, less than 13 in this case. So I can choose 2. So what is the formula looking now in this particular case? So in this particular case, the formula will look like this. So this is the recurrence formula. So I have x0 equals to 2. That's the seed. And the next number, this is what it says, the next number is equal to, take the previous number, multiply by 4, add 3, and take the remainder of that when you divide it by 13. So that's basically applying the formula with a, b, m, and x0 are plugged into this recurrence formula. So basically you make a choices for this number, this multiplier, this increment, and the modulus. And so from there, we will have to start doing our computation. So we already know where to start. So that's the seed. That's why we need the seed to know where to start. The next number in that sequence will be x1. So let me write down. So what is x1? According to the formula that I have right here, this formula, it says x1, which is my next number, is equal to 4 times the previous number. So 4 times the previous number, but the previous number was x0, plus the increment, plus 3, and then I take the modulo, or to the remainder of that divided by 13. So let's see what that is. So from this formula, of course, I know what x0 is. x0 is 2 because that's my seed. So if I write this down again, so it's going to be 4 times 2 plus 3, and that's going to be modulo 13. Okay, if you simplify this number inside this parenthesis, you're gonna get 11 because that's gonna be 4 times 2, that's 8. 8 plus 3, that's 11. So you're gonna get 11 modulo 13. And remember one of the properties I mentioned a little bit ago. If this number here is positive, and this number is positive, and this number is less than the modulus, then you get back this number. So that will be 11. So this is going to be equal to 11. So what happened here? What happened here is that we computed x1, and x1 here happens to be 11. Right? So that will be the next number in that sequence. Now, the next number in that sequence will be x2. So what is x2 here? So x2. To compute x2, I have to go back and look at the formula, what the formula says about what x2 is. So I'm going to scroll up here. Okay. This one right here is my formula. So what is x2? x2 is going to be 4 times the previous one. The previous from x2 is x1. plus 3 mod 13. So according to the formula, if I go here, so it's going to be 4 times the previous number, which is x1. I add 3 because that's the number I have to add, mod 13 again. Right? So I know already what is x1, so I have to just replace it. So I have 4 times 11, because x1, remember we already computed x1 is 11 here, plus 3, and that's gonna be mod 13. Okay, so I need to simplify this expression here, 4 times 11 plus 13. If you do that, that's gonna give you 47, because it's 4 times 11 is 44 plus 3, that's gonna be a 47. So that's gonna be a 47 mod 13. Now in this case, I don't have any properties here, so what I really need to do in this case is I need to take the number 47 and divide it by 13. So what I have to do there is take here on the side, if you wish, you take number 47 divided by 13, whatever the remainder of that division is, that's gonna be this whole expression here. 47 mod 13 is the remainder of that division. Okay, so I'm not gonna go into the details. You go ahead and double check that that remainder is actually 8. Okay, that number right there is gonna be my next number in that sequence. So x2 will be 8. Okay, I'm gonna do one more. So just to emphasize how the method is. So once I have the x2, what happens here is, let's see. Let me put this in a box here. Put it in the box. So what's gonna be my x3? So my x3, in this case, the next number, will be equal to my previous number times 4. It's gonna be 4 times my previous number, which is x2, plus 3, and I had to take that mod 13. So it's gonna be mod 13. Okay, I already know what x2 is because I computed it here already. So this is gonna be equal to 4 times 8 plus 3, and that's gonna be mod 13. Okay. So that's gonna be my next number in the sequence. So in this case, the x3 will be, then if you actually do it, so let me do a little bit faster here. So it's 8 times 4, that's gonna be 32. Okay, plus 3, that's gonna be 35. So basically what you're gonna get in here is equals to 35, and then 35 mod 13, and 35 mod 13 is gonna be 9. So that's gonna be the next number in the sequence. The next number in the sequence will be 9 in that case, in this particular case. I had to stop the previous part of the video because I didn't have enough room to keep writing. So this is a continuation from the example we were doing, and I remember that we started with the seed 2, then we got this next number in the sequence was 11, then the third number in the sequence was 8, and the last one, the fourth number we computed, was the number 9. And of course you continue this way and you can generate a pseudo-random number sequence here. So if you continue that way, this is what's going to happen. So you're going to end up with this sequence. Of course, this is the seed 2, then 11, then 8, then 9, and then you will get 0, and then you will get 3. Now, let's notice something important here in this sequence. If you look at these numbers, and I'm going to mark them with color here, this sequence that is here, that sequence repeats itself again over here. So you see the pattern there is exactly the same. It's at 2, 11, 8, 9, 0, 3, 2, 11, 8, 9, 0, 3, and that's gonna keep happening forever. So it doesn't matter how long you go, you're gonna have that pattern. So what that actually means is that we have a cycle. This is what we call a cycle. So this random number generator, it has a cycle. It has a cycle. And basically what that means is that you're going to have pseudo-random numbers, but after some period, and this is going to be the period, you're going to repeat again and again and again and again forever. Now, that's not very good if you are trying to generate pseudo-random numbers. The thing is, if this period is long enough, let's say the period is about 1,000 or a million or 100,000 million, in real applications, like when you have to model something, it won't really matter that you have a cycle, because if the cycle is long enough, then that's okay. Now, the problem with this particular example is because the cycle here is very short. It has 6 numbers. So the cycle here is 6 numbers. You have 6 numbers in the cycle. So this pseudo-random number generator will be okay as long as the cycle is long enough for what we need to do. Now remember that this is not cryptographically secure, so we won't use this for cryptographic applications. But if you want to simulate some kind of random numbers, then this will be okay, as long as, of course, your cycle is long enough to produce the pseudo-random sequence. For example, a million. The cycle is, for example, a million positions. Now, that could happen. The other thing that could happen is something similar to what happened in the middle square. Now, remember that middle square was stuck in the number, for example, 0, 0, 0, and didn't go up from there. Now, what's going to happen here is, if you sometimes for some choices of A, B, M, and the seed, you're going to get stuck in a number. So let's look at this particular example. So in this example, I have the seed is going to be 2, and I'm making these choices. 6 is for the multiplier, 1 here for this number, and the modulus is 32. So if you start generating numbers like that, so I'm going to just do a couple of things here and I'll show you what happens there. So if you do x1, so x1 will be 6 times x0 plus 1 modulo 13. Of course, I know what x0 is. X0 is just the 2, so it's going to give you 6 times 2 plus 1 modulo 13. Right. So what happens there is you get, that's modulo 32, right? So I'm just thinking about the previous example. So instead of 32, I'm doing modulo, this is modulo 32 here. That's modulo 32. So what I'm going to get here is 13, of course. So 6 times 2 is 12 plus 1 is 13. And then 13 modulo 32, because 13 is less than 32, then this gives me 13. Okay. So that will be the second number in my sequence. So x1 will be 13. And you compute the other numbers in that sequence as well. So I'm just going to write down the first few numbers in that sequence. So you start with the seed, which is 2. We computed 13. If you go ahead and compute the next one is going to be 15, 27, 3, 19, 19, 19, and so on and so forth. So in this particular case, for the choices of A, B, M, and the C, this sequence here will repeat itself. So it will be stuck at 19 forever. So that's also not very good. So it's not good that we want to generate pseudo-random numbers, but for this particular choice of A, B, and C, we're getting not really something very good. The other case where we have a cycle is a little bit better, because the cycles repeat. In this case, the number 19 is just stuck there forever and ever. So that's not very desirable here in this particular case. So so what are the problems here with the linear congruence generator? So one of the problems we saw in one of the examples is that it is cyclic. Cyclic means there is a cycle there. So you start with numbers, look the pseudo-random, but then the cycle goes again. It repeats forever and ever. Another problem what we just saw there is for particular choices of A, B, M, and the seed, the sequence produces the same number every single time. Now, that does mean that the linear congruence generator is really bad. It's not really bad, really. What you need to make sure is when you make the choices here, so we going to start with x0, which is your seed, and then the xn plus 1 equals to a times xn plus b modulo the number m. The key part here is you want to make choices for the numbers x0, because that's what you usually do, a, b, and m, in such a way that two things happen. One is that the cycle is long enough for applications, and two, that you make sure that there is not such a place where the number repeats itself. Now, there are choices, we can make some choices for A, B, M, and the Z that's going to make that happen. And there are some mathematical properties that the numbers A, B, M, and the Z need to have in order to avoid those kinds of problems. So the seed should be chosen in a particular way, the cycle should be long, and there shouldn't be any numbers that where the sequence is stuck there. One of the things that you actually have to do to make sure that the cycle is long enough, M should be a large number. So M should be chosen to be large. M should be large. And should be large. That's large here. Because the thing is, the reason is the following. The cycle is always less than m or equal to m. So if you have a cycle that is m, you know, whenever you're doing this recurrence formula here, when you're doing the linear congruence, you know that the cycle is always going to be less than this number m, less than or equal. So if this number is long enough and you make the choices of A, B, and the x0 properly, then you're going to make sure that exactly this guy, the cycle here is going to be long enough. If you choose m to be, for example, 4, then your cycle is less than or equal to 4, which is not very good. A cycle of 4 elements is not good. But if you choose m to be a really large number, then at least you know that you have a possibility of your cycle to be really big. So that's all I have to mention about this linear congruence generator. So in the next video, we're going to talk about what is the what we do in Java to generate pseudo-random numbers, and also most importantly, how do we generate cryptographically secure random numbers. So I'll see you in the next video.